Now let's consider vibrations from the quantum mechanical point of view. Not as classical, but quantum. So basically, we're talking about the second equation of the Born-Oppenheimer approximation, which relates to the wave function of atomic displacements. So in the harmonic picture, when we neglect non-adiabatic effects, we arrive at the following Schrödinger equation for that wave function. So this wave function of atomic displacements is the total energy. The first term is the kinetic energy, and this is the potential energy in the harmonic approximation. So we expand the potential energy around the equilibrium positions on a given potential energy surface, and therefore there is no linear term. All right. So in order to solve this multivariable Schrödinger equation, we will make a change of variables. So what we shall do, as we kind of did in the classical case, although I didn't show you this explicitly, we will perform a transformation from atomic displacements to their specific linear combinations, which we call normal modes. And in this new representation, we will find that this Hamiltonian of the quantum mechanical system of these atomic vibrations can actually be represented as a sum of individual independent harmonic oscillators, and that would allow us to solve this equation exactly. Okay, so in order to fulfill this program, what we shall do, we shall recall that instead of the force constant matrix phi, we can introduce a massively scaled matrix, which we call dynamical matrix. It's exactly the same as in the classical case. And then we shall write the potential energy of our system, which is a quadratic form in terms of this vector of these displacements, in a matrix form in which we collected all the elements of the force constant matrix into this matrix phi, and all the displacements into the vector column u. So this is a transposed one. So this expression is a scalar. Then in that expression, we shall replace phi with d using this definition of the dynamical matrix. And then we will collect, we will combine rather, m in the power 1/2 with the ut and m 1/2 with the u. And at the same time, we shall replace the matrix D itself by its representation here using its eigenvalues, which are squares of the frequencies, and eigenvectors, which are y lambda. And we sum over all solutions of this eigenvalue eigenvector problem for the matrix D. We have done this already. And this is a called spectral theorem, which allows representing any square matrix by its eigenvectors and eigenvalues. Once we have done this, we can take this sum out and collect all terms by a scalar small y lambda. And again, we did discuss this before when talking about stability. And this scalar y lambda is a specific linear combination with respect to atomic displacements u. And this is its precise explicit expansion shown here with the coefficient given like that. So this is a linear combination of atomic displacements, and this is a normal mode as such. And we see that potential energy of our vibrating system is given as a sum over all normal modes of our system with omega squares, the vibrational frequencies, and this normal mode displacement. So each normal mode, lambda, corresponds to displacements of all atoms of the system. This is it's a collective displacement, as opposed to displacing just one atom when just one ui would be non-zero. So in that case, when y lambda is engaged, is excited, then all atoms displace in some particular way. Remember how we discussed normal modes for a linear molecule and for a water molecule. So this is a very general notion. When the normal mode is excited, all atoms move in a particular way. So this is how we transform the potential energy into new coordinates y lambda from an old one, which are u, the atomic displacements. In order to transform the whole Hamiltonian, however, we need also to deal with the kinetic energy operator. In the kinetic energy operator, Pi is the operator of the momentum for the degree of freedom I, and it is related to the displacement, the coordinate of that degree of freedom, via this well-known quantum mechanical expression. So if we would like to replace displacements with new coordinates y lambda, we have to find a replacement for the momentum pi, which would be conjugate to this new displacement coordinates. The new coordinates and the old coordinates are related via this linear expression, and therefore that partial derivative can be easily written via the chain rule as a sum of derivative over all possible y lambdas for all possible coordinates. That particular partial derivative, it follows from this formula. It will basically be this coefficient. So it's easily calculated, and then we arrive at that formula here. Let me just take this a little bit away. Okay, like this. And minus IH, and this derivative can be considered as a momentum P lambda conjugate to the coordinate Y lambda. So the relationship between the old momenta and the new momenta are given here. Now we can take this expression and substitute it into the kinetic energy. And the calculation is very simple. So what we need to do, we take this kinetic energy and replace Pi with that sum. We have a double sum over lambdas, which can be easily simplified. And the reason for that is we see that the masses cancel out, and then the sum over I can actually be collected here. And what we have a sum over all i's, keeping lambda and lambda prime fixed. But this is nothing but a dot product of two eigenvectors, y lambda and y lambda prime. And we know that eigenvectors are normalized and orthogonal, and therefore this sum must be equal to the chronicle symbol. As it is equal to the chronicle symbol, this double sum becomes a single sum, lambda equal lambda prime, and we arrive at the following result. So we see that if the potential energy is represented as a sum of individual potential energies for each normal mode, kinetic energy follows suit. It's also given as a sum of kinetic energies of each normal mode with the unit mass. Combining these two results together allows us to replace this Hamiltonian, which was originally written via our old coordinates, displacements and momenta, via new coordinates. And now, because these two terms are represented as a sum of individual terms for each lambda, we can also write this Hamiltonian as a sum of individual terms. And if you look at this particular expression here, you will notice that this is nothing but an energy or Hamiltonian of a single harmonic oscillator with a unit mass. So, our Hamiltonian of the whole system of vibrating atoms in the harmonic approximation has been shown here to be can be rewritten as a sum of independent harmonic oscillators. So we know from quantum mechanics, if the Hamiltonian is a sum of individual terms, then first of all, the total energy would be a sum of the energies of eigenvalues of each of those individual Hamiltonians, and the wave function would be a product of wave functions for each individual Hamiltonian. We know that for a single harmonic oscillator associated with the index lambda, the total the eigenvalue is written as h omega n plus 1/2, where n is an integer number changing from 0 to plus infinity. It gives us an excitation of this harmonic oscillator. So the total energy would be a sum of such energies, and therefore we see from here that the total energy of the system of harmonic oscillators is specified by a collection of these numbers and lambda, which corresponds to the excitation of each particular individual harmonic oscillator. So a collection of all these numbers would give us a description of each particular state of the harmonic system. And when all these numbers are all equal to 0, we will have the lowest possible state or in energy of our harmonic oscillators, the ground state. And the wave function of this collection of harmonic oscillators, as was already said before, will be given as a product of wave functions for each particular harmonic oscillator. So this is a wave function of the harmonic oscillator lambda in the state n lambda, when n lambda has a particular value. So we have a product of all these states. And again, we see that we managed to solve this rather complicated Schrödinger equation for a collection of harmonic oscillators by means of a very special transformation from old coordinates u to new coordinates y lambda, and that allows us to fully characterize the solutions of that equation, both the total energy and the wave function.